Give me 1 or 2 minutes more to have more student, and then I will start it. All right, let me start my lecture. So, inshallah, you and all of your families are fine during these challenging conditions, and everyone are in good health. Actually, after sometimes we have returned to the class, so I know topics 1 to 6 have been already completed, and I would like to begin topic 7. In this lecture, we will explore the fundamental of how electrical power is transmitted from generation resources to end consumers efficiently. This lecture will cover both HV transmission system and LV distribution networks and highlighting their components, operation, and design principles. We will discuss here the modeling of transmission lines, analysis of power flow. However, you already saw in other module EE 451, but I will show you some brief explanation. And then the role of substations and protective devices. And additionally, let me add a new student. All right. Additionally, this lecture will address key challenges in modern power system, including reducing losses, maintaining reliability, and integrating renewable energy resources. At the end, um, hopefully, you will have a comprehensive understanding of the structure, operation, and management of power transmission and distribution systems. Let me add a new student. All right. Okay, you can see the outline of the lectures in this slide. In this lecture, as I told you, we will cover the following main topics. First, I will provide a brief introduction to power distribution systems, discussing their role in delivering electricity from substation to end consumers. Next, we will examine the classification of distribution systems, exploring different types of network configuration and their characteristics. We will then discuss design considerations in distribution systems, including voltage levels, load requirements, and safety measures. And following this, we will perform distribution system calculations such as load flow, voltage drop, and losses estimation, which are essential for efficient and reliable system operation. Finally, we will study a single line diagram SLD of some primary and secondary distribution feeders, helping to visualize the network structures and understand the connection between the various components. Okay, the distribution system is the part of the power system responsible for delivering electrical energy to consumers for practical use. It connects the substation, which is fed by the transmission system to the consumer's meters, and a typical distribution system generally consists of three main component feeders, which carry power from the substation, and distributors, which deliver power to different areas or loads, and finally, service main, which provide the final connection to individual customers. And understanding the structure and operation of distribution systems will be so essential for ensuring reliable and efficient power delivery. This is just a brief introduction, and this figure is showing a simple distribution system showing the connection between a substation, feeders, distributors, and consumer loads. The substation receives power from the transmission system and steps it down to a suitable voltage for distribution. Feeders carry the electrical power from the substation to different points in the network, and from the feeders, distributors branch out to supply power to various loads such as residential or industrial or commercial consumers. The most important point here is that the voltage is will be further reduced to service levels, typically from 11 kilovolt to 400 or 230 volt, depending on the we are talking about single phase or three phases. Before reaching the customers meetings, we will have some step down transformer to provide this level of the voltages for customers. And this structure ensures an organized and efficient distribution of electricity, minimizing the losses and maintaining reliable supply. So we can also call this one as a single line diagram, but later on we will see that what the single line diagram is exactly. All right. Distribution systems can be classified based on the several criteria. First, they may be categorized according to the nature of the current, such as AC or DC systems. Second, classification can be based on the type of construction, which refers to whether the system used overhead lines, underground cables, or the combination of both. And finally, distribution systems are classified according to the scheme of connection, which defines the network configuration, such as radial, loop, or network systems. Understanding these classifications help us in designing efficient and reliable distribution systems to a specific load requirements and operational conditions. Okay. This slide explains the classification of electrical distribution system based on the nature of the current. In general, distribution systems can be divided into two main types, DC systems and AC systems. Historically, both types were used, but today AC distribution systems are mostly universally adopted in most of the countries. And this is mainly because AC systems are simpler in design, more flexible for voltage transformation by using of transformers, and more economical for transmitting power over long distance. As a result, AC systems have become the standard choice in modern power distribution network at this moment. Okay, this slide introduced the classification of the distribution systems based on their type of construction. In practice, electrical distribution network can be installed either as overhead system or underground systems. Overhead system are typically more economical and easier to install and maintain, making them widely used, especially in rural or and suburban areas and most of the cities. You can see the overhead systems. On the other hand, the underground systems offer better reliability, improve safety, and enhance visual appearance, but they involve higher insulation and maintenance costs. So we have to, and also um, underground cable make the system uh, more beautiful in comparison to the overhead systems. So therefore, the selection between these two types of construction depends on several factors such as cost, reliability requirements, environmental conditions, urban planning constraints, and um, aesthetic considerations, environmental beauty and so on. Okay, this slide highlights two important factors influencing the choose between the overhead and underground distribution systems. One of them is public safety and initial cost. Another one is initial cost. From a safety perspective, underground systems are generally more secure because all electrical conductors are buried below the ground, significantly reducing the risk of electrical contact, electrical faults, and hazard to the public. However, these advantages comes up with a major drawback in terms of cost. Underground system in the other sides require extensive civil work such as trenching. You need to dig the ground and make some trench, and installation of conduits, specialized cables, and manholes, which makes their initial investment significantly higher than the overhead constructions, and often 5 to 10 times more than overhead systems. As a result, while underground systems offer improved safely, their high installation cost is a key consideration in making a decision to have which kind of construction is better to be used. All right. This slide discuss two additional factors in comparing overhead and underground distribution systems: flexibility and fault occurrence. Overhead systems offer much greater flexibility because their components such as poles, conductors, and transformers can be relatively easily relocated or modified to accommodate changes in load demand or network expansion. In contrast, underground systems are less flexible since infrastructures like docks and manholes is fixed once installed, making future modifications more difficult and more higher costly. On the other hand, underground systems have a clear advantage in terms of reliability, as the likelihood of faults is significantly lower due to better installation and protection from the environmental factors like wind, or humidity, or sunshine, and other environmental factors. This makes underground systems more robust, although less adaptable compared to overhead systems. All right. This slide focus on two practical consideration in distribution system design. appearance, and fault handling. Underground system provide a clear advantage in terms of aesthetics, as all cables are hidden from view, resulting in a cleaner and more visually appealing environment, as I mentioned before. So everything is hidden underground. So this has led to increasing public and urban planning pressure on utilities to adopt underground installation, especially in cities, inside the cities. However, when it comes to fault location and repair, so you need, you need a major devices, is expensive, and finding the fault location also is a expensive process, and underground system presents significant challenges here. Although faults are less frequent, detecting and fixing them is more complex, time consuming, and costly due to the increasability of cables. In contrast, overhead systems allow for quick fault identification and easier repairs because the conductors are visible and readily accessible, making maintenance operations more efficient and more benefit. All right. This slide also compare overhead and underground systems in terms of current carrying capacity and voltage drop. Overhead conductors generally have a higher current carrying capacity because they are exposed to air, allowing better heat dissipation. This enables them to carry more current for the same conductor size compared to underground cable, because underground cables are we are putting underground cable under the ground, so um, 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 distribution of um, the heat of cable is more difficult. That's why less current will pass through the underground cable in comparison to overhead cables. In contrast, underground cables have limited heat dissipation due to insulation and surrounding soil, which reduce their current carrying capability. However, underground cables offer and advantages in terms of electrical characteristics, as their conductors are placed closer together, resulting in lower inductive reactance. So this leads to reduced voltage drop and improved voltage regulation compared to overhead systems. This slide highlight the comparison between the overhead underground system in terms of useful life and the maintenance cost. Underground distribution systems generally have much longer service life, often exceeding 50 years, because the cables are protected from environmental factors such as weather, pollution, and mechanical damage. In contrast, overhead systems are more exposed to external conditions and typically have a shorter lifespan of around 25 years. Additionally, underground systems require significantly lower maintenance costs due to their reduced exposure to fault caused by wind, ice, lighting, and traffic-related incidents. On the other hand, overhead systems demand more frequent inspections and repairs, making their long-term maintenance more expensive despite their lower initial cost. So we need to find a compromise between the overhead and underground systems based on their advantages and disadvantages. So this slide also discusses the issue of electromagnetic interface with communication circuits. Overhead distribution systems can create interface with nearby telephone or communication lines due to electromagnetic coupling. In such cases, the power line currents may include unwanted voltage in communication circuits, which can distort signals and degrade the quality of communication. And this can even raise the potential of the communication channel to undesirable levels. And in contrast, underground distribution systems largely eliminated this problem because the cables are shielded and buried, reducing the electromagnetic interaction with nearby communication lines. And as a result, underground systems are more suitable in areas where reliable communication infrastructures is very critical and very important. Okay, this slide also provides a general conclusion on the choose between the overhead and the underground distribution systems. In most cases, overhead systems are widely adopted because they are more economical, flexible, and easier to install and maintain. However, underground systems are used in specific situations where overhead construction is not feasible or is restricted by local regulations. So this typically includes uh, populated urban areas, locations with strict stochastic requirements, or places where safety and reliability are higher priority. Therefore, the selection of the distribution system is not only a technical decision, but also depends on legal, environmental, and social considerations. Okay, this slide introduced the classification of distribution system based on the scheme of connection. In electrical power distribution, the way in which feeders and loads are interconnected plays a crucial role in system performance, reliability, and continuity of supply. Based on this, distribution systems are generally categorized into three main types: radial system, ring main systems, and interconnected systems. Each configuration has its own advantages and limitations. For example, radial systems are simple and economical, while rings, main, and interconnected systems offer high reliability and better load sharing. And understanding these schemes is very essential for designing efficient and reliable distribution networks. And you need to understand what are their advantages and disadvantages. So based on them, you can utilize them to apply for one specific applications. All right. This slide also describes the radial systems of distribution, which is the simplest scheme of connection. In a radial system, individual feeders extend outward from a single substation and supply power to distributors from one end only, meaning that each load is fed through a single pass. This configuration is typically used in situations where power is generated at a low voltage and the substation is located near the center of the load area. Due to its simple structure, the radial system is easy to design and economical to implement, but it has the limitation of lower reliability since any fault in the feeder can interrupt the supply to all downstream consumers. Okay, this slide highlight the advantages and drawbacks of the radial distribution systems. One of its main advantages is that it is the simplest type of distribution circuit, which result in the lowest initial cost compared to other systems. However, it has several important limitations. In this configuration, the section of the distributor closest to the feeding point carries the highest current and is therefore more heavily loaded than the rest of the line. Additionally, the system relies on a single feeder and a single distributor, which makes it less reliable. If fault occurs in either the feeder or the distributor, the supply is interrupted for all customers located behind the fault as there is no alternative path for power delivery. So this makes the radial system less suitable for application where high reliability is required. So this is, I think, one of your questions in um, uh, last year. It was one of the question for final exam. So you need to write what is the advantages, drawbacks of different types of the configuration. So, all right. This slide also continue to explain additional limitation of the radial distribution system. Customers located at the far end of the distributor experience significant voltage fluctuations, especially when the load on the system is changing. And this is due to a voltage drop along the length of the distributor, which becomes uh, more uh, more reliable with distance and varying load conditions. As a result, voltage regulation at the distant end is poor, affecting the quality of supply. Because of these issues, along with the system limited reliability, the radial system is generally suitable only for short distance distribution applications where voltage drop and load variations can be more easily managed. All right, this slide introduces the ring main system of distribution. In this scheme, the primary windings of the distribution transformers are connected in the form of the closed loop, forming a ring. So later, I will show you the. I think you already saw the all of the type of this distribution configuration. So one of the questions will be, for example, in your final exam which of the following singular diagram is representing the ring or um radial distribution configuration. So you have to choose uh, one of the single line diagrams. So the loop originates from the substation bus bars, extend through the service area, and then returns back to the same substation, creating continuous circuits. This is the main feature of this type of distribution configuration. This configuration allows power to be supplied from two directions, improving reliability and voltage regulation. The single line diagram typically is showing how the substation feeds a closed feeder loop, such as the LM NOPQRS pass, ensuring that loads can be supported even if a section of the network is disconnected or experience a fault. So here you can see the this loop. So as I mentioned, this loop is representing to LMN or PQRS. So this is a loop. So if you have a fault in somewhere, the customers can be supplied by other paths. So this slide is showing a primary ring distribution system, a reliable method commonly used in electrical power distribution networks. In this configuration, power is supplied from a substation into a closed loop or ring feeder that connects multiple load points through distributors and distribution transformers. So the ring structure allows electricity to follow in more than one direction, which significantly enhance system reliability. If a fault occurs at any point along the ring, that section can be isolated without interrupting the entire supply, and power can still reach customers from the opposite direction. So key components shown include the substation as the main source, the primary ring forming the closed loop distribution transformers, stepping down voltage, and distributors delivering power to end user. And overall, I can say that this system ensures continuity of service, flexibility in operation, and improve fault management compared to radial distribution system. In generally, we can say the reliability of the systems can be improved better. Sorry, 1 minute. All right. This slide explains how distributors are connected in primary ring distribution systems and highlight its key advantages. The distributors are trapped from different points along the feeders, especially at points um, M, O, and Q through distributions transformers. This arrangement ensures that loads are supplied from multiple points within the ring. So one major advantage of this system is that it results in a minimal voltage fluctuation at the customer's terminals, so providing more stable and consistent power supplies without any interruptions. Additionally, the system is highly reliable because each distributor is effectively fed by two feeders, namely SLM, this feeder, and SRQ this feeder. So we have a two feeder, this one and this feeder. This dual supply path allows electricity to reach the load from alternative directions in case of the fault, and ensuring the continuity of services and reducing the likelihood of power interruptions. I already told you what does that mean, likelihood, right? It means that the probability of the uh, power interruptions, you know. All right, this slide describes the fault handling capability of a primary ring distribution system and how it ensures continuity of supply. In the event of fault occurring on any section of the feeder, the systems can maintain uninterrupted service to customers. For example, if a fault occurs at point F here, so along section SLM in this feeder, um, so that particular section can be quickly isolated from for reparation or maintenance. And despite this isolation, power supply is not disrupted because electricity can still reach all connected loads from these feeders, you know. So um, the key feature of this system is that power can circulate around the ring from either substations, allowing for efficient load sharing and improve voltage regulations. If one substation or feeder section becomes unavailable due to fault or maintenance, the other substation can continue supplying the entire network. So this dual source arrangement significantly enhances system reliability, flexibility, and continuity of service, making interconnected systems highly suitable for critical and high demand areas. Okay, this slide explains the configuration and advantages of an interconnected distribution system. In this arrangement, distributors are connected to different points on the feeder rings, especially at O, P, Q, and R through distribution transformers. These transformers step down the voltage from the primary feeder to a level suitable for customer distributions, and by tapping the ring at multiple points, the system ensures that electrical loads are supplied more uniformly and flexibly. And one of the main advantages of this interconnected system is the significant improvement in service reliability, because the feeder ring is supplied by more than one generating stations or substation. Power can be uh, reroute from one alternative source if one section is unable to meet demand or experiences in a fault, and we have alternative routes of electrical networks. So during peak load hours, areas that are normally supplied by one generating station can be supported or completely fed by another section, and this load sharing reduces the need for large reserve generating capacity and improves the overall efficiency and economic operation of the power systems. All right, this slide introduces the key design consideration in a distribution system, emphasizing the importance of maintaining good voltage regulation. Voltage regulation refers to the ability of the system to keep the customer's voltage within accessible limits under varying load conditions. It is one of the most critical factors in ensuring high quality and reliable electrical service to customers. So to achieve this, careful design of both feeders and the distributors is essential, and feeders must be sized appropriately to carry the expected load without excessive voltage drop, while distributors should be designed to ensure uniform voltage levels across all points of consumptions. So proper planning, selection of conductor sizes, and system configurations, all of them are playing a vital role in minimizing voltage variations and maintaining efficient operation of the distribution networks. Okay, this slide focuses on the design consideration for feeders in the distribution systems. A feeder is primarily designed based on its current carrying capability, meaning it must be capable of safely carrying the maximum expected load current without overheating or causing damage to the conductors. In this case, voltage drop along the feeder is considered less critical compared to its thermal capacity. So the reason for this is that any voltage drop occurring in the feeder can be effectively compensated using voltage regulating requirements installed and at a substation, such as tap changing transformers or voltage regulators and so on. Therefore, the main priority in feeder design is to ensure adequate conductor size and capacity to handle load demand, while voltage control can be managed separately at the appropriate substations. All right. This slide also explain the design consideration for the distributors in the distribution systems. And unlike feeders, a distributor is designed primarily based on the voltage drop rather than current carrying capacity. So this is because distributors directly supply power to customers, and voltage at the customer's terminals must remain within specified limits. So there are uh, um, uh, some regulations that restrict voltage variations, typically within plus minus 6% of the rated value. Therefore, it is essential that the design of the distributor, particularly its size and length, ensures that voltage drop along the line does not cause the customer voltage to fall outside these permissible limits. So proper selection of conductor size as well as controlling the length of the distributor helps maintain stable voltage levels and ensures reliable and high quality power delivery to end user. Okay, this slide introduces the topics of distribution system calculations, which uh, plays a crucial role in the proper design and operation of electrical networks. In this section, both current and voltage at different points of the systems are systematically calculated, and these calculations help you analyze how power flow through feeders, distributors, and loads under different conditions estimated. And the main objective is to ensure that all currents and voltages remain within their permissible limits. So this is important to prevent overheating of conductors, avoid excessive voltage drops, and maintain safe and reliable operation of the system. By performing these calculations, you can verify that the network is properly designed, identify potential issues, and make necessary adjustments to improve performance and ensure compliance with standards. Okay, in this slide, I want to introduce the concept of distributor feed at one end. In this configuration, the electrical distributor is connected to the power supply at only one end, while loads are connected at various points along its length. As electrical power flows from the feeding point toward the for and the current gradually decreases because part of the load is trapped off at each intermediate point. So this means that the section closest to the supply carries the highest current, while sections farther away carry progressively less current. So understanding this current distribution is essential for proper design, voltage drop analysis, and ensuring efficient operation of the systems. So I want to stop up to here and come back again, just 10-minute break and please join to the next session to the new link.